So on our warm-up today, a quick review of 6.3. Does the table represent linear or exponential? Notice here you're adding one, so you're increasing by a constant. On your independent, so your dependent, looks like you're multiplying by 3 every time. That is exponential. It's linear if you're adding down there. Okay. Evaluate the function for x. You're going to go ahead and put that 2 in for the x value right there. So you get 5 times 3 to the second, which is 9, or 45 there. 9 times 5 is 45. Okay, and graph the function, compare the graph to the parent function. So I have the graph of that one. You may have used your graphing calculator on it, but on that graph, the parent function of this is g of x is equal to 2x. You just drop the a term, make the a term 1. Okay, the graph of is a vertical stretch by a factor of 2.5. That's what the a term's doing. Okay, and the domain is all real numbers there. Range is y is greater than 0. All right. Probably did not get to the other ones there, so we are going to move on. I want you to take out yesterday's assignment, please, before we start up our lesson. Page 185 of the Student Journal. Today we're going to be talking about exponential growth and exponential decay, as well as we're going to touch on the compound interest formula, which is actually dealing with exponential growth. Okay? Okay, done talking. Pay attention. Okay? Focus back there. Thank you. All right. Once again, just like always, you can kind of summarize the lesson at a later time with your vocab terms there. But they give you the notes on the bottom here, and they talk about an exponential growth formula. Now, I'm going to try to point out the similarities between your growth formula and your decay formula. There's your decay formula. Okay, it's on the next page, top page 186. Okay, before I point out the differences, I'll put them both up there so you can see them both at the same time. I want you to just talk with your, I know that's kind of small, you may have to flip back and forth in your book, but I want you to talk to your neighbors there and point out what the differences between a growth and a decay function are. It's not a big difference, okay? And I'm going to focus in on the growth function to deal with this, and I will write the decay one right next to it. Okay? But with growth function, you have this, y equals a times 1 plus r, and I'm going to, rather than calling that t right now, I'm also going to name it x. Okay, not like x, our buddy back there, but x, the variable x. Okay? It's the same thing as x. So, like if I was doing the decay function, what was the only difference with the decay? Good. R is being subtracted rather than adding. So you could have an x right here instead of a t. And the reason I like showing that is because every graphing pattern that we study, there's always an independent variable x and a dependent variable y. Okay? There is an x and a y in here. The t represents x. In math, when you're dealing with the variable t or time, that is an independent variable. Almost always. Okay? It's not always, but almost always. So whenever you talk about time, that replaces the letter x. And that's what they've done here. Just so you're aware of that. Because I want you to start thinking, hey, this year I've studied this form. What is that? Oops. That is linear. Y equals mx plus b. Notice we need to know m and b to write the equation. X and y always stay x and y. Okay? When we're dealing with this one or the growth one, we need to know which two variables in order to write an equation. Yeah? You need to know r and a. R is your rate. A is your initial amount. We also know A as our y-intercept. That's how we talked about it with our graphs. When you were graphing yesterday, say, hey, look, that's your y-intercept. It's our initial amount. We've also talked about A as our speed limit or our stretch and shrink. It does all of those things. Okay? We just use different names for it and talk about what it does differently depending upon the context we're in. When we're graphing, it's our y-intercept. When we're doing a story problem, it's what we start with. Okay? When we're graphing, it's also our stretch and shrink factor. Okay? All of those things are what A stands for. Yes? It wouldn't be H because you'd have to have X in it. H would end up here with the X. It would have to be in the power position. R is just your rate, and it's a rate in decimal form. So like, you guys got a rate on your paper today. Okay? It was a rate in percent form. Tell your neighbor what your percent on your paper today was. Okay, so let's talk really quick about percent. Someone give me their score out of 21. Was it out of 15? All right, let's change that. Out of 15. Okay, 13 out of 15. 13 divided by 15, what is that? Okay, 0.86666, so let's call it 0.87. All right, and so I'll make that a little more clear. 0.87. That is decimal form. That is your rate. Now, what do I tell you guys to change that to? The percent. How do you get to percent? Okay, good. Some of you say move the decimal 2. Some of you are saying multiply by 100. It's the same thing. That brings it to percent. Quick review, the word percent means per 100. That means you have 87 per 100 problems. If you had 100 problems using the rate you came up with here, you probably would have got an 87 out of 100. 87%. That's what the word percent means. It is 0.87. Okay? That is your decimal rate. So, if I tell you your percent is 92%, what is that in decimal rate form? Tell your neighbor, please.
0.91, right?
Okay, 92 over 100 or?
I thought you said 91, so
0.92. Okay? All right, got it? So, if I'm dealing with growth, I'm adding a rate to 1. Why 1?
Because 1's our favorite number today.
When I'm dealing with decay, I'm subtracting a rate from 1. Once again, why 1? What does 1 represent? Yeah, hey, in percent, 1 represents 100. You'd move that 2 over, right? So if I have 100% and I'm subtracting an amount from it, 100% in decimal form is 1. I'm subtracting a percentage from it. Okay? So when I'm dealing with growth, I'm adding a percentage, an amount to it because it's growing. That's like your bank account. You want to be adding a rate to your bank account. If you're subtracting a rate, you won't have much in your account for too long. That's why when like the stock market goes down and people start freaking, that's why. Okay? When your value's appreciating or going up, you're adding an amount. When it's going down or depreciating, like you buy a car and you drive away, the value of the car just dropped a lot. A lot of money. Okay? So, it's going down. The rate's going down. So what we're going to do is we're going to apply these to some different practices. Here we go. Number 1 on page 187. In 2005, there were 100 rabbits in Polygon Park because it's mathematical. The population increased by 11% per year. First increase, is it growing or decaying?
Growing.
It's growing.
More bunnies.
Okay, write an exponential growth function. Okay, so we have to figure out our variables. Jill pointed that out earlier. It's 1 plus r, all to the power of t. Okay, the 11%, that is our A or R. That's R. What is R? It's 11%, which is 0.11. Okay, so if I'm plugging this in here, A or R is 0.11. We have plus 1. What's A? Yep, it's our initial amount, right? So in this case, we start with 100. Okay, what does T stand for? Time in years. In this case, years after 2005. Okay, so this...
As far as we're concerned with this problem, 2005 is the dawn of time.
Correct. 2005 is the starting of time according to this problem. Now, so really, your equation could be this. Now, I'd be kind of upset if you left it like that because I want you to do the math in here. And it's not that difficult of math, right? We can call that y equals 100 times 1.11 t. And notice we can't figure out t until they tell us how many years after 2005 we're dealing with. Right now, it's just t because we don't know. However, in part B, they tell us. Okay? I want you to figure out the answer for part B, please. Just rabbit. Round to the nearest rabbit. Okay?
That's the 806 rabbits then.
That sounds kind of sad, but you know, we don't want any partial rabbits running around.
But that makes great dinner.
All right. 2005 to 2025 is?
20 years.
20. T equals 20 there because we're taking 2025, subtracting 2005. That gives us our T value. So in this case, T is 20. Okay? So we put the 20 in. What do we get? 806? Is that to the nearest rabbit? Yeah. All right. It's like point what?
Unless you want .26.
Yeah, we don't want that. We don't want to hear about rabbit horror stories. Okay?
It's not horror. It's like really big.
Sure. They're eating rabbits?
Good
No,
dogs.
they're chasing after them. They can't catch them.
All right. Oh, so they're getting exercise. Nice of the rabbits to help.
They weren't bad in the first place. Okay, let's just stop talking.
All right. All right. Hey, number 2, determine whether the table represents growth or decay or neither. Go ahead and talk with your neighbors about it.
Now,
Okay, number 2, excuse me. We're going up 1 here. What are we doing here?
we're making a rabbit cake.
So you guys, you've been kind of spoiled. We've had you deal with real easy numbers like 1, then 2, then 4, then 8, then 16. You're like, oh, dude, they're multiplying by 2 every time. Okay. Well, it's not always that easy. And what you have to do is try to figure out what they're actually multiplying by. So if I gave you an easy pattern, right, and let's just say x goes up by a constant, and I gave you this, okay, you could say, hey, every time I'm multiplying by 2. Well, mathematically, the way you actually figure that out, hopefully you just look at it and can know that. But if you don't, if the numbers aren't easy, then how do I get 2 from 8 and 4?
You divide 8 by 4.
I divide 8 by 4. How do I get 2 from 4 and 2?
Divide 4 by 2.
Divide 4 by 2. And how do I get 2 from 2 and 1?
Divide 2 by 1.
Divide 2 by 1. So I divide the second by the first. So if I divide 30 by 20, I would get 1.5. Thank you. If I divide 45 by 30, do I get 1.5? If I divide 67.5 by 45, do I get 1.5? Yeah. And so that's the process you have to go through. You know, really, you're not going to have easy stuff like this. You're going to have more complex stuff. But we start with the easy so you can do the complex. Make a note to yourself, hey, to find out that ratio, I've got to divide those two numbers. Okay, the second by the first. Okay, so this represents what? Growth or decay? Growth. Why growth? 1.5 is so or decay.
It's a very happy number.
It's larger than 1.
It's larger than 1. Okay? If it's bigger than 1, it's growth. If it's less than 1 but greater than 0, it's decay. Okay? There we've got growth. How about this one?
That is decay.
What are they multiplying by? 1/4. Okay? Multiplying by 1/4 every time, that is decay. Because I wasn't calling you my cuz, I'm just saying because 1/4 is less than 1. Right? That's cuz. All right. How about number 4? What does that give me? That's not 6. It's, flip it over. What's 2 divided by 6?
It doesn't go, but it goes in, right?
That's 1/6, right? Is this going to be 1/6? Nope. So this is neither. Not even a pattern there for it.
So it's like that's a linear. You can tell it's like.
Yeah, it's subtracting 10 every time.
Yeah.
Well done. That is linear.
You get extra credit now.
No, but good job. I'm proud of you. You impressed me. You impressed me. I know that would make you happy. All right, let's move on. Number 6, 7. Tell your neighbor if it's growth or decay, and then identify the percent of increase or decrease, the percent of change there.
Okay, 6. I'll answer like
Okay, 6, growth or decay?
growth.
That is decay because, not decay because B is less than 1. What's the rate of, we're dealing in percent. Notice it says percent. What percent did it go down? 5%. So the percent of change is 5%. It's not 95%. It's 5%. You always start at 1. So make a note to yourself. Start at 1. That will be a common mistake that many people make. Start at 1 or start at 100. It's a 5%. So number 7, growth or decay? Growth. What's the percent increase this time?
108.
Always start at 1. So it's just 8. Yep. It's how much you move from 1. This one's a little tougher, growth or decay? This is decay. What is that in decimal form? 0.75. Therefore, it is a 25% decay. Okay? So note to yourself that, hey, it's 1 minus what, if you want to think of it that way, is equal to 0.75. That might be making it a little more complex. So you're just saying, how much am I going down to get to that? And on this one, you're saying, how much am I going up to get to that? Okay? And then change it to a percent form. All right. Any questions there? Sarah? No? All right. Hey, we're going to come back to number 9 and 10 tomorrow. Okay?